Hello, you are muted.
Good afternoon.
Afternoon. Okay, so in today's lesson, we're just going to be continuing with chemical bonding since it's a big concept, like there's a lot of subtopics. And I drew up some notes on Lewis structures. Um, because I know last lesson we ended off with covalent bonding between, I think, carbon dioxide, and you had a bit of a problem with that. So I brought you more of that and those type of examples because, quite honestly, they won't ask you to be showing covalent bonding between hydrogen and chlorine, examples that you've done tons and tons of times. Mostly they'll be asking you to do examples on something you haven't done. I don't know about your examiner, but if I was the examiner, I would think like that. I mean, then what's the point of learning, right? If I ask you what you've done in class, you need to
Mhm.
apply your knowledge. So today we're just doing Lewis structures, and then we'll see how the lesson goes to move on to maybe valence electrons and so on. So Lewis structures, Lewis notation uses dots and crosses to represent the valence electrons on different atoms. By now, you should know that valence electrons are the electrons in the outermost energy level, and then they participate in bonding. Do you know why they are the only ones that participate in bonding? Why there are other electrons as well? Why do valence electrons only participate in bonding?
I don't know.
It's a very important question. So why do valence electrons only participate in bonding? It's because, let me put it to you this way, that when you start with energy levels, like the first energy level will have the least amount of energy. The electrons in the lower energy level will have the least amount of energy. Then the second energy level will have a little bit more. Then the third energy level will have a little bit more. And the fourth energy level will have the most energy. I'm talking about electrons because electrons only participate in bonding, not protons, not neutrons, because electrons can only move. They
Yeah.
can be transferred. So, valence electrons participate in bonding because participate in bonding because they have more energy. Have more energy or the most energy um, as compared to the electrons that are closer to the nucleus. We will be doing a structure of the nucleus in this lesson because I want to explain to you something very important about those nuclei. So, valence electrons on different atoms, the chemical symbol of the element is used to represent the nucleus and the inner electrons of the atom. So, this is just a simple example. We have a hydrogen atom with one valence electrons would be represented like this. Okay, so we have hydrogen atom, this is the element basically, and then this is the valence electron. So, based on your knowledge, can you represent hydrogen cyanide in Lewis structure form? Hydrogen cyanide consists of hydrogen, carbon, and nitrogen. Do you think you'll be able to do that? You need to show me the
No.
bonding between hydrogen, carbon, and nitrogen at the same time. And obviously, this molecule is a compound is hydrogen cyanide. So, you begin by writing down the element, the symbol of the element, and its valence electron. So we will represent the valence electron by a little dot. And we know hydrogen has one valence electron because it is in group one. Okay. Some of these valence electrons should be on your mind. Okay. So carbon has four valence electrons, and nitrogen has how many? It has five. It has five. Yeah, it has five. So let's draw it properly how it is would be depicted. And these are five valence electron, okay, of nitrogen. So let's look at the main atom, which is carbon over here. And let's put carbon as well. Um, rearrange the electrons to be what it should be. So this is what um, it's going to look like because hydrogen needs one valence electron. So, and carbon has four valence electrons. These ones are going to end up sharing. Okay, so these ones are going to end up sharing. And then you have, you know that carbon has given, or well, not given exactly, but shared its one valence electron over here. So how many valence electrons will carbon have left now?
Three.
Three. So just going to put it here like this. And then now nitrogen has five valence electrons and it needs um, three to achieve stability. Because in chemistry, all elements are trying to achieve stability, right? So it needs five valence electrons, three valence electrons to reach stability, and carbon needs around two. So what will happen is that nitrogen and carbon will end up sharing as well. No transfer will happen here. Okay, so they end up sharing, and then let's see if we're obeying the octet rule. What is the octet rule? The octet rule is that the elements in the second energy level should be able to, in their last outer energy level, which is the outer energy level, they should have eight electrons in their orbital. So eight electrons. But the group one, which is hydrogen and helium, they have maximum of two electrons in their energy level, and then they will be satisfied. Okay, so take that in for a minute, what I just said. Okay, and now we have hydrogen cyanide. So now what are we going to do? We're going to inspect. We call we're going to inspect. Okay, we have hydrogen here. Hydrogen is in group one. It needs a maximum of two electrons to be considered stable or to be happy. Okay, so hydrogen has one, two. Okay, great. Now let's see carbon. Carbon needs how many valence electrons? How many electrons? Eight electrons to be happy, right?
Yes.
So 1, 2, 3, 4, 5, 6, 7, 8. Does carbon have 8 electrons? Happy.
Yeah.
Now nitrogen also needs 8 electrons to be happy. So 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen is also happy. Now you know you can get like 3 marks for this particular question because you have satisfied all elements. Okay, So this is how you're going to end up doing hydrogen. And the Lewis structure is very important to be right. We use crosses and dots to represent the valence electrons. And once again, why do valence electrons participate in bonding? Because they have the most energy. Those electrons have the highest energy, and they are able to participate in bonding, because obviously bonding requires a lot of energy. To form bonds requires a lot of energy, and bonds, when bonds break, they also release energy. You will learn that in a later stage in maybe grade 11, about endothermic and exothermic reactions, and also bond forming and bond breaking. Okay, now we have bonding and lone pairs. Bonding pairs, they are different, right, as compared to lone pairs, because bonding pairs are electrons that are shared. So if I have to see, um, in this particular case, all of them are participating in bonding, okay, with the exception of this one here. It's not being shared. So the shared, um, shared electrons are called bonding pairs, okay? Bonding pairs. And then the ones that do not get involved in bonding, like in this particular case, these two were not involved in bonding. These are lone pairs. You will be asked, how many lone pairs does nitrogen have? You can't say, oh, well, it has 5 valence electrons, so it has 5 lone pairs. No, 3 of these electrons are bonding pairs. I mean, three has 3 bonding electrons, and then it has 2 lone pairs. So I hope you are able to like understand what is bonding pairs and lone pairs, because it's very important. So let's look at an example. Molecules such as CO2 and H2O are formed through covalent bonding. One of the above molecules does not have lone pairs of electrons on the central atom. Choose the correct Lewis diagram for this molecule. So if you have to draw the structure of carbon dioxide, the Lewis structure, I mean, so let's take blue, carbon dioxide. It has 4 valence electrons. And oxygen has how many valence electrons? 6 valence electrons. So 1, 2, 3, 4, 5, and 6. Same thing on this side. 1, 2, 3, 4, 5, and 6. Now, let's look at this carbon dioxide molecule on its own. Okay, so I'm just going to use a different color to show you the bonding pairs. Which electrons are participating in bonding? You must ask yourself that to find out how many lone pairs or what are the lone pairs. Let's look at how many electrons are participating in bonding. We have 1, 2, 3, 4, 5, and 6 that are participating in bonding. These are called bonding electrons. Because aren't these being shared? Because if you look at oxygen, 2, 4, 6, 8, oxygen is satisfied. Let's look at carbon. Okay, 2, 4, 6, 8. Carbon is also satisfied, and oxygen, which is the same thing as the side, is also satisfied. So once it's satisfied, then you can go ahead and take out, identify your bonding or your lone pairs. So now tell me, how many how many lone pairs does carbon have? How many
Zero
lone pairs?
does not have lone pairs.
Good, does not have lone pairs. Then how many lone pairs does oxygen have? Or we're only going to look at one oxygen because it's literally exactly the same thing on either side. How many lone pairs does oxygen have? Huh?
Two.
2, not 4. two lone pairs. Okay, you know it. Um, okay, now I want to take you to the periodic table that I have here to show you something that might help you understand bonding better. So before I start, I just want to write down something over here. Okay, so we're going to write down the goal. Every atom, or you can say element, is trying stability. What do I mean by stability? That it must satisfy its rule, its requirements, its given requirements. For example, now I wanted you to have a look at these numbers here. Let's just annotate it from here. Okay, these numbers. What are these numbers? This is, by the way, like the periodic table that you guys get in your paper. So what do these numbers represent?
The groups.
Yes, the group. The group number. Okay. Now we have group 1, group 2, group 3, group 4, group 5, group 6, and group 7, group 8. Now, secondly, these are non-metals. You're going to write down, like the best way to distinguish or do this is to create like the step form. And obviously, hydrogen is a bit of like a rebel. It's also a non-metal, it belongs there. The rest of them on this side, on your left side, are metals. Now, this is very important because you might be thinking, why is it important to learn which ones are metals and which one aren't? It's very important um, in knowing what type of bonding. So, for example, if you have a non-metal and a non-metal, what type of bonding is that? Non-metal and non-metal being bonded together. Take an example and see. We have hydrogen being bonded with chlorine. What type of bonding is this? Covalent. So it has covalent bonding. And this happens between a non-metal and a non-metal, which is, for example, hydrogen, and any of these, literally any of these elements that it will bond with, if it's sulfur, nitrogen, oxygen, fluorine, anyone, it will be covalent bonding. That's how to identify whether this particular molecule will have covalent bonding or ionic bonding. Now, a non-metal and a metal will have ionic bonding. Why? Because there's a difference. There's a huge difference in either electronegativity or the fact that an ionic bonding results in what being formed. An ionic bond results in, I'm trying to write this as neat as possible, results in a salt. In other words, it's what? A non-metal and a metal. For example, sodium being a metal plus chlorine. This is a metal, this is a non-metal.
Mhm.
It forms what? Sodium chloride. What is sodium chloride? Table salt.
So,
The salt that you have for lunch or is put in your food, that's sodium chloride. Now, if you look at it differently, you see that sodium has a number here, a fancy decimal number. What is that decimal number for? It's the electronegativity. So this is the electronegativity of sodium, and then let's go all the way to chlorine, is 3.0. So if the difference is, I think, more than or less than 2.5 or something like that, let's just check the numbers again. But if there is a significant difference, then the bonding is ionic bonding. So sodium and chlorine will never have sort of covalent bonding. They won't share electrons. Either one of them will either transfer, or sodium being the one who will transfer the electron to chlorine, which has 7 valence electrons. Okay, so that's that about nonmetals and metals. Um, okay, now I want you to look at this. I'm looking at it horizontally. Horizontally, these represent energy levels. Energy levels, okay? And I'll tell you what I mean by that. Energy level. So this, for example, is the second energy level. I mean, the first energy level, just the first orbital. This one will be the second one, and this one will be the third one. So let's, for example, a draw an example of element in this one. Let's take lithium, for example. Okay, so lithium has, um, I'm gonna do it here. So lithium, for example, has a positive nucleus because it has protons and neutrons, and there's no electrons found in the nucleus. Okay, so it has a positive nucleus. Surrounding it, because lithium is in the second energy level, so number one, and then lithium is here, it will have two orbitals. So orbital one, oh, yuck. So it will have orbital one, okay, and orbital two. Okay. Now, look at how many electrons lithium has. It has 3 electrons. Well, it has 3 protons, which means 3 electrons, because this atomic number here is actually the number of protons and not electrons. But protons are generally equal to the electrons if there is no charge on the element. So, for example, if lithium had a charge of +1 or -1, or like for example, Na is +2 or +1, then it would not be considered that it has the same amount of electrons and protons, which we will learn later on if we're covering formal charges. But for now, we are looking at lithium, which is a normal neutral element, and it has 3 electrons. Okay, not valence electrons, it has 3 electrons. Okay, so how do we know where to put them in our orbitals? Because you can't just put them anywhere. It will be marked wrong because remember, the element, it's very specific. The structure is specific to the element. So how do we know where to put them? So lithium has 3 electrons. So look at the first energy level. It's 1, 2. So that means in the first energy level, which is this, we won't count this one. This is just the nucleus. Don't get confused. This is not an energy level. This is just a small nucleus. So we have the first energy level and it has a maximum of 2 electrons. It cannot take more than 2 electrons. If you put 3 electrons here, 4 electrons, it will be marked wrong because the first energy level can only carry a maximum of 2 electrons. That's why when hydrogen bonds, hydrogen is satisfied with 2 electrons, it is stable just like helium. Look at helium. Helium has a maximum of 2 electrons. This is stable. For helium, it's stable. He's happy. But hydrogen has 1 electron. So it always tries to achieve what? Stability. Every element is trying to achieve stability. Stability, right? So where was I? Okay, so lithium has 3 electrons, so 1, 2, and then we're going to put them in the first energy level because hydrogen is in the first energy level, and lithium is in the second energy level. So now we're looking at the second orbital. How many electrons are left after 2 electrons? It has 3, so how many electrons are left? It has 1 electron left. Okay, so we're going to put them here and then remember to put the minus inside the electrons. So that's one way of figuring out how many valence electrons, because if you look at it, valence electrons are the electrons that are in the outermost energy level. For lithium, this is the outermost energy level, this part here, this last orbital. It's the last orbital, and that is the last basically energy level. So that electron that you see, um, this electron, it has the most amount of energy and it's likely to participate in bonding as compared to these electrons, which are closer. So remember, the nucleus is positively charged, and by the laws of physics, positive attracts negative. So the nucleus is going to have a strong attraction to these 2 electrons. It's not going to let it go easily. But between this one, the nucleus, and this one, it's not that of a strong attraction. So that's why these electrons will have energy to leave somewhere else as compared to these ones that are tightly bound to the nucleus. That's why this electron participates in bonding and is a valence electron. So that is lithium. Now let's look at, just for another example, let's look at something in the third energy level. So let's look at sodium. We have sodium. Okay, so I'm going to do sodium here as well. Sodium, first, every element has a nucleus. So we're going to write down the plus sign here for sodium. Now, sodium is in what energy level? It's in the third energy level. Here's the third one. Okay, so it's in the third energy level, so that means it will have 3 orbitals. So it will have its first energy level or orbital, it'll have its second energy level and orbital, and then it will have its um I draw it like that, but this is completely wrong. It should be completely round. Let me see if I can try again. No. Okay, there we go. So that is how much. We're not going to count the nucleus. That is 1, 2, 3 orbitals. It's in third energy level, so that's great. Now, compared to the rules of the third energy level, it's not the same as the second energy level and the first energy level. Okay, so the third energy, oh wait, so the second and the third, they have a sort of what you call this limit where you can either every element is basically given an option. Okay, let's call it an option for you to understand better. So they're given an option of what? It says you can either, like, let me give you an analogy. So, like, your teacher comes up to you and says, okay, you can either get 50% to pass and go to the next grade, or you can excel and get 90% or 100% and be also going to the next grade. Okay, so in one case, she's telling you you can do the bare minimum and pass, which is great for you. You can just pass, and or you can also get 90% and pass and go to the next grade, get promoted. But what's the difference? There's no difference because, anyways, if you get 50% or you get 90%, you're going to go to the next grade. It's a different thing if you are going to do better and then get a good job, if you're going to get a good degree and so on. I'm not talking about that. I'm just talking about one which is doing the bare minimum and the other one which is excelling, but the outcome is the same. Okay, don't get me wrong, I am not trying to influence you to just barely pass. Okay, but it's just an analogy. So similarly, in elements, we have options too. The option given to these elements is either you achieve stability by gaining the bare minimum, which is 2 electrons, and satisfying the first energy level, which is helium. You basically take helium as a role model. He took just 50% and he passed. Or you can take the octet rule, which is 8 electrons in your outermost energy level, get a 90%, and also be stable. Okay, so they get an option. So, for example, lithium, it will be easier for him to lose the electron and go to energy level 1, which is basically a maximum of 2 electrons in your outer energy level to satisfy your hunger. But oxygen doesn't have the same requirements, and these are based on their capabilities. Okay, so oxygen will try to achieve 8 electrons. Instead of losing the 6 electrons that it has, he will try to gain 2 more electrons to fulfill stability. But look at lithium. Lithium can't go ahead and gain how many electrons does it need? Just 5 more electrons just to satisfy itself to get to the octet rule. No, no, it rather lose one. So it's rather settle on the 50% than do a whole lot of work to get to the 80 or 90%. Okay, so that is the fact that they're given options. Now let's go back to sodium. Sodium has 11 electrons, okay? Has 11 electrons and it is in the third energy level. So now let's count. Has 1, 2. So it can only put 2 in the first energy level. So let's put 2. In the second energy level, you can have 8 electrons, a maximum of 8 electrons. So 11, it has 11. So it's going to have 1, 2. Now let's count. 3, 4, 5, 6, 7, 8, 9. So 1, 2, and then 1, 2, 3, 4, 5, 6, 7. So it's going to have 7 electrons in the second one. So you can put them anywhere around here. One, you can put them singly first, and then you're going to put them as together. So I'll show you now what I'm doing. 1, 2, 3, 4, 5, 6, and then you can put like 7 over here, like that. And then it has how many electrons left? After 7, it has 1, 2, 3, 4, 5, 6, 7 electrons. It has 4 more electrons. So it's going to go ahead and put it here. Okay, the remaining 4 electrons, which is 7 electrons. Wait, hold on. It's totally wrong. Let's just try to fix it from here. So it's going to actually have bonding electrons because it's a sodium. So we're going to start off with 2. That's fine. I'm just going to change my color because it's confusing me. And then you're going to start off with putting, you can have a maximum of 8 electrons, not 7 electrons, 8. So 2. You're going to put them singly first, by the way. Don't put them like how I'm putting them. So you're going to put them singly, 1, and then you're going to start filling the double until you reach the maximum energy level for the second orbital. So it has 2, 4, 6, 8 electrons. Great. Okay, in the second energy level, because the second energy level can accommodate 8 electrons. After 8 electrons, how many electrons are left? So now it has 2, 4, 6, 8, 9, 10. 10 electrons. It has 1 electron left. So it's going to put it in the last energy level. So it's true to say that sodium has 1 valence electrons. And this is proved by the orbital system and the energy level system. So in this particular case, now that sodium has 1 valence electron, do you think it is better for it to, do you think it's better for it to bond with give off its electron or get another electron? What do you think it will do? It has an option. It has 1 valence electron. So is it going to give off its electrons or go ahead and collect 7 more electrons?
It'll collect.
Yes, it's going to collect. It's going to collect from whichever thing it's bonding. Let's say it's bonding from chlorine. No, did you say it's going to collect? That means it's going to gain electrons. Think about it.
It's gonna.
It's going to lose. It's going to give off 1 electron. Because you're saying, if you're saying it's going to collect electrons, you're saying instead of losing 1 electron, it's going to gain 7 electrons. That's a lot of work for sodium to do. So sodium is gonna try, it's gonna, get away from that. It's gonna run away because sodium is not a high performer. Sodium says rather I will get 50% to pass rather than go and do the hard work to get 90%. So it's gonna give off 1 electron. It's gonna sit easy, smart. I'm gonna give up my 1 electron instead of going and doing the hard work to gain 7 electrons. Do you understand what I'm saying now? So this is the orbital of sodium telling us what it's going to do. Okay, so yeah, this was basically the explanation about this. Let me see if I left out anything. Okay, the thing about valence electrons and valency. Do you know what is valency and what is valence electrons? Are they the same thing? So they're definitely not the
I
same
don't
thing.
think.
You have, okay, let's go back to our whiteboard. Okay, so actually gonna open our existing whiteboard. I don't know why I opened a new one. Just click the link again when you like when it ends on its own.